It's 11 o'clock, so we can start. Can you please start recording?
Yes.
Good morning, everybody. And today, you hear me well, right? Actually,
Yes.
I would be grateful if you show your faces because it's much more convenient to explain when I see your reactions. Otherwise, the impression I have an impression I am speaking with the wall, which is not good. Okay, so today for the beginning, I would like to tell to show what happens in the problem number 2. But unfortunately, I realized that video online, okay, online demonstrations have some specific requirement, and sometimes what is visible during in-person demonstration, it's not really visible when we are using the camera. So I modified the experiment a little bit to make it more visible online. So the question was, so in the problem, the teacher put the iron, a piece of iron, actually iron nail, into hydrochloric acid, and we see there are a lot of bubbles. The nail interacts with the acid, and bubbles are sealed. Does everybody see the bubbles?
Yes.
Good. Either show these or say it out loud. And the question was how to make, and the second demonstration was to put copper into the same acid, actually copper wire. So, and there is no reaction, no bubbles, no interaction. And if copper really interacts, oh, I forgot to turn it off. Okay. If the copper really interacted, what would we see? What we would see the green formation of green color, blue-green color, because dissolved solubilized copper ions are blue-green. But we see no color change, so no bubbles, no reaction. And that was actually, if you do this, if you do that in parallel, you see that there are bubbles. Oh, okay, let me make it more concentrated because I'm not sure. Okay. Fresh solution. So again, no reaction with copper, and the nail is fizzing and bubbles are forming, some gases forming. And if you leave it for a while, leave the nail for a while, then take it out, wash and wipe with a paper towel, we will detect the change of the mass. The mass will become smaller, and this is the measure of the reaction rate. So, for example, if for 1 hour the mass drops by, I don't know, 1 gram, that's an indication of the reaction rate. So the question was, the teacher asked students how to make this reaction faster. And I tried to demonstrate what exactly the teacher would suppose to do, but it is not, this process is not visible on camera. It's not easy to see. So I decided to modify the experiment a little bit, and I replaced copper with platinum, the platinum wire, which is, platinum is also non-reactive with hydrochloric acid. I put to the acid, and no bubbles, no reaction at all, because platinum is known to be king of all metals. It's a noble metal. It is not reactive with anything, virtually anything, and that is not a big surprise. However, when we do this, I connect the platinum wire with the nail, and I even do this to make the contact more. That's just a metal iron wire to make the electric contact more reliable. And then I put, can everybody see each step? Is it visible? So I took, so this is just the metal wire which I used to make this contact tight, and this is a kind of a holder. This is a platinum wire, which is not reacting with hydrochloric acid. You see, no reaction. No reaction. And this is a nail, which, as you know, does react with hydrochloric acid. Now I do this. I put both ends. And what do we see? Can anybody describe it? Can anybody unmute?
Bubbles coming from both metals.
Yeah, actually the bubbles are coming from both platinum and iron. And if I remove, and what does it mean? Does it mean platinum started to react? It doesn't. It doesn't. And in reality, iron reacts faster. And if you leave it for 1 hour and measure the weight, the mass of iron, we will see it lost more mass than without platinum. But if we check the mass of the platinum wire, there will be no change. That means no reaction between platinum and hydrochloric acid. So platinum is not reacting, but some bubbles are forming on its surface. And iron is reacting more actively, but the bubbles are forming less actively. In reality, if the electrical contact would be perfect, there would be no bubbles on the iron surface, and all bubbles would form on the platinum surface. So by doing that, we achieved what exactly what the teacher was supposed to demonstrate, that without changing the composition of the solution, the teacher accelerated the reaction of the iron nail with the hydrochloric acid. The same, actually, the same process can be observed with copper, but it is much less kind of evident. It's much more difficult to see. That is why I replaced copper with platinum. But in principle, the situation, the processes are the same. And what happens? To explain that, we need go back to okay, Anar, host 11, please. Can you enable screen sharing? Anar, are you here?
Yes, I just did that.
Yeah, thank you. Because Anar is a host, he is recording this video, and I cannot do anything without his permission. So you remember then when we put the piece of iron into solution, into water, HCl, whatever, doesn't matter. The solvent is supposed to be H2O. What happens? Iron ions start to dissolve double charged ions. But the electrons do not. They stay in the piece of iron. That means after each ion leaves the piece of each ion of iron leaves the piece of iron, the iron becomes double negative, because two positive charges escaped from this piece, and this piece becomes positively negative because electron stays there, and their charge is not compensated anymore by iron, by this iron ion. That means the electrical field forms which holds dissolved iron ions near the surface of this piece. So we have the so-called ion code. That's what I already explained last time. And at equilibrium, the density of these ions in this code is achieved some equilibrium density where the rate of escape of iron ions and rate of return are the same. But what if some other ion returns back? What if some other ion is present? For example, H+. If we have HCl, we actually have a mixture of H+ and Cl-. If H+ is more actively taking electrons than iron 2+, then they are more likely to come and pick the electron. But this hydrogen becomes neutral, but it is not metal. It is not depositing on the surface, because if iron ion takes back the electrons back, it deposits on the surface as a solid. It returns to the solid state. But hydrogen is not solid. Hydrogen is a gas. So when hydrogen atom forms, it cannot become a piece of this iron, the part of this iron piece. Instead of it stays on the surface until it meets another hydrogen atom, and then they recombine and form the hydrogen molecule, which when many molecules form, the bubble of gas forms, and finally the bubble of gas goes up and escapes to the atmosphere. That is what happens. That is what happens if we just take a nail and put it into HCl. The second part of the story, what happens with the copper or platinum, no matter. If we put platinum or copper, okay, let's be platinum, it also dissolves. It also forms platinum ions, actually double charges, and also the iron coat also forms. But platinum is going to a solution much more reluctantly, because it does not. It is holding electrons much more tightly, and the electrons are holding platinum ions much more tightly. That means this rate, the rate of escape, is much slower. The density of these ions is much lower, and the potential, the voltage between the positively charged ion coat here and the rod itself is lower. So here the voltage, if we using some magic to measure the voltage between this layer, the coat, ion coat, and the rod, the voltage is high, the big voltage. Here the density of ion is small, so the voltage is low. And when hydrogen ions try to pick up electrons from platinum, from the excess electron density from platinum, they can't do it, because platinum ions are much more avidly take electrons back, so they are competing with H plus much more successfully. So no hydrogen forms in that case. Now let's redraw the same picture again. So we have a piece of iron, and we have a piece of platinum. We have a dense iron coat here, and a very low density iron coat here. So we have a big voltage between this coat and the iron rod, and we have a low voltage here. But if we put these two ions into a single beaker, the same solution, that means this is conductive. So which means we kind of connect these two coats with the conductor. So the potential of this coat and this coat is the same. That means the potential of the iron coat, iron rod is much higher. The electronic density here is much higher. So we have a lot of huge excess of electrons here, and just a tiny excess of electrons here in the platinum. And what happens if we connect these two pieces with the conductor? The excess of electrons from here will start to flow to there. That means this piece of platinum will become we will get an additional negative charge. Now let's take a look what happens here when the surface becomes additionally charged. So this is a platinum surface, and this is a solution. So we have a coat of ions, of platinum ions, but it's very, very tiny. So this is a solid. And we have excess of electrons. We have a lot of electrons here, which were withdrawn from iron. So obviously, this will greatly accelerate the process of return of platinum ions back, because now they are much, much more strongly attracted by the metal. So all platinum ions come back and stick to the surface, become neutral. But that does not resolve the situation, because there are just a small amount of platinums in the solution. And what happens when all those ions return back? This piece still contains excess of electric density, electric charge. That means when hydrogen ions will start to come, they pick these electrons and become neutral. The hydrogen ion becomes neutrally charged as a single charge, neutral charged atom. Each of them meet another single charged atom. They form a hydrogen gas, a hydrogen H2 molecule, and it is this hydrogen which we see as bubbles when iron and platinum are connected. Does it make sense? Did everybody understand that? Okay. But why does it accelerate the process? There are two reasons. First, platinum is more active in withdrawing electrons than hydrogen, which means the negative charge is being removed constantly from iron, and which facilitates the solution of more and more and more iron ions. That's the first, the first effect. The second effect, when hydrogen gas forms, it kind of, when it forms bubbles on the iron surface, it kind of protects the surface from the contact with acid. And it also kind of decelerates the process. When the part of hydrogen is formed outside or somewhere else, that makes the iron surface more accessible to HCl, so the dissolution becomes faster. And there is one story when on the eve of metallurgy, aluminum metallurgy, when aluminum was where there was no reliable technology for preparation, for large-scale preparation of aluminum metal. One American millionaire decided he ordered the yacht for himself, a large boat, made of aluminum, to show how rich he is. And he also requested that all rivets there was no welding technology for aluminum at that moment. And the yacht, the boats were usually assembled using rivets, not welding. And he requested all rivets to be made of copper. Because it was very, very aesthetically, I don't know, beautiful, silverish aluminum and yellow-red copper. It was shiny. It was absolutely spectacular picture. And this yacht went to the first, when it went to its first marine journey. It lasted just few days, because who can explain what happened next?
It probably sank.
Yes, but why? What exactly happened?
It was too heavy, or the aluminum reacted with the copper.
Yeah, but why? Elizabeth.
Dissolved.
Yeah, Elizabeth, you want to say something?
I just want to say that there was a reaction and the.
Yeah, because aluminum started to dissolve near the points of contact with rivets, and the boat literally fell apart after a few days, and that is exactly what we have here. Okay, and the rest are other parts of the solution. I think they are clear from the text. Actually, today I just wanted to make this demonstration. But if you have questions regarding the solution, feel free to ask. No questions. So the solution is clear, right? The official solution. Okay. Now let me tell about today's topic. Today's topic is redox reaction, reduction oxidation reactions. And these reactions are somewhat different from we discussed before. We know, we all know the electrolytic dissociation theory, and we know that salts or ionic compounds, when they are soluble, they fell apart in the solution, and when they react, they just interact as separate ions, and they just regroup. And well, I can demonstrate. I can do one demonstration to show this idea. So we have one. Okay. Let's take. This is just water. The example of the soluble salt is the, okay, let's take barium chloride. It's like calcium chloride, but the experiments with it are much more spectacular. So let me. This is just a white solid, which is pretty soluble in water. I'm going to make a solution in water. Let's wait until it dissolves completely. So this is the again, this is the barium chloride. So when it dissolves, we have a barium chloride, and the dissociation. So this solution is accompanied by dissociation. We have one barium ion and two chlorine ions, and nothing else. As you can see, this is a clear, nice, clear solution. And I take another solid. And this solid is ammonium sulfate. It's also salt. Yeah. Salt, which is pretty soluble. I use the electrical stirrer because just to save time. Actually, it's a fancy stuff, but I can use the just store it using this spatula, but that's more convenient. So again, we have a clear solution. And the process is NH4. NH4 is a composite ion which behaves like sodium or potassium, a single charged positive ion. So we have when it dissolves, we have two ammonium ions. I took ammonium instead of sodium because it's much easier, much faster, dissolves much faster. So it saves our time. So in summary, we have 4 types ions, and what now I do, that's the first solution, and that's the second solution. Now I'm going to mix them. We have a white solid, which if I leave it, it will precipitate, and we have a solid on the bottom. Like looks like a milk, but it's a solid. I can filter it, I can dry it, and it will be just a solid, non-soluble in water. What happens? How do we explain that? That explanation is quite simple, and it is in line with what we know about ions. This ion and this ion, they form a dense connection with each other, and they form the crystals that are fully soluble. That means if we mix these two solutions, these ions will precipitate in the form of barium sulfate, which is absolutely insoluble in water, very, very insoluble. And the other two ions stay in the solution. They are not participating in the reaction. And that is again, that is totally consistent with what we know about reactions of ions. However, there is another reaction which is not easy to explain using this approach. Let's make another solution. This is a solution of sodium sulfide, not a sulfate, but sulfide. Sulfide means sulfur. There are 2 oxygens in the molecule, not 4. Like sodium sulfate, sulfide is greatly soluble in water. And I'm going to make this solution right now. That is solution number 1. Now let's make a solution number 2. The solution number 2 will be potassium permanganate. Potassium permanganate is my lovely chemical. When I was a school student of your age, I loved to buy it in pharmacy. And so it's very, it used, now it is, I don't know if it, if they sell it. In the past, it was used as a local antiseptic, usually for treatment. You make a solution. Now you will see why I love it. So this is also a solid salt, but it is it forms very intense solution of very, very nice color. And I very loved to, I loved very much to see how it dissolves. I love this color. So, what do we have here? Here we have sodium sulfide, sulfide, not sulfate, SO3. Dissolves in water, and also dissociates like sodium sulfide, sulfate, or ammonium sulfate. And potassium permanganate dissolves in water to form potassium, 1 potassium ion and 1 permanganate ion. So, so far everything looks pretty much the same as the previous case. But that is not, it is not that easy. Usually we observe some reaction between 2 salts when one new salt precipitates. Otherwise, just the all 4 ions will be kind of coexisting in solution, and that's it. And we will see no reaction, no change. But what if I mix this solution with that solution? actually the color changes, and if you, it is not blue anymore. You see, it's kind of a gray, dark gray. And if I leave this solution for a while, some solid will precipitate, some brown solid will precipitate, but this solid is not okay. This solid is neither it's hard to explain. Because violet color belongs to this ion. You see, we see this color in the solution. This color belongs to this ion, and if we have just a regrouping of ions, it is not clear why the color is supposed to change like this. But the situation becomes even more interesting if we do the following. I add a little bit of acid here. I add a little bit of acid from the previous story. So this is sulfate plus acid, and add this solution to permanganate. Okay, more acid. The color is totally disappeared. No color at all. So the question, what happened to this ion? If this ion is dark violet, how does it happen that this ion disappear, the color disappear? Does it mean that means we have no just regrouping of ions binding to each other in different combinations. We have something else. We have kind of a destruction of this ion, disappearance of this ion. To understand that, we need to understand the concept of reduction and oxidation. Because the word oxidation, it's easy to see the word oxidation has the same root as oxygen. And oxidation originally was under oxidation, people originally meant a reaction of something with oxygen. And the typical example of oxidation is a combustion. For example, when methane is a natural gas, methane is burning, they have a lot of heat, and we see a fire. So we usually under oxidation we mean some violent reaction where a lot of energy forms. But what is the source of this energy? Where this energy comes from? To understand that, let's take a look at the process of oxidation of methane, CH, and let's draw all chemical bonds explicitly. So this is a methane, natural gas, and it reacts with the oxygen molecules. Actually, the 3 oxygen molecules are needed. 3, 2, correct? Okay, let's check. And we form 2 molecules of H2O, right? We get these, and one molecule of CO2, CO, O, O. Yeah, 4 atoms, 4 oxygen atoms here, and 4 here, 1 carbon and 4 hydrogens. Yes, this is the process of combustion of oxygen. Now let's, but where the energy comes from? Why we have so much of heat in this reaction? This is obviously this is due to some change, but what change occur in the structure of those molecules? If we count the number of bonds, 1, 2, 3, 4, 5, 6, 7, 8 here, and 1, 2, 3, 4, 5, 6, 7, 8. So there is no change, right? So no extra bonds are formed, no existing bonds disappear. There is just a regrouping of bonds. So this hydrogen was connected to carbon. Now it is connected to oxygen. This carbon was connected to hydrogen. Now it is connected to oxygen. And it would be natural to propose that it is the change of the nature of these bonds which leads to formation of extra energy, to release of extra energy. But why does it happen? To explain that, we need to understand the concept of electronegativity. I don't know if you know, if somebody told you about that, but it is natural to usually it is they tell it without explanation. Some atoms holds their electrons more avidly than others. Some atoms are more willing to donate electrons than others. Why does it happen? What is the reason? The reason is as follows. Consider the hydrogen atom. Oh, okay, not hydrogen. Okay, carbon atom and oxygen atom. There are 2 electronic shells in each of those atoms, and we actually ignore the inner shell. There are 2 electrons on the inner shell, electronic shell, and these 2 electrons, they kind of screen 2 positive charges of the nucleus. So we can consider this as a core. So the electronic shell plus a nucleus form a core of each atom. And we can just ignore, because it's very, very dense, very chemically imperturbable. So we cannot change it by chemical means. And it is convenient to consider that carbon core is a ball with 4 positive charges. And the oxygen is the same, the ball with 6 positive charges. And there are 4 electrons on the outer shell, in the outer shell of carbon, and 6 electrons in the outer shell of oxygen. Now, the question is, which of those atoms hold their electrons more tightly? And why and why? To answer this question, we need to understand what is the reason, which force keeps electrons near the nucleus. Obviously, this is an attraction Coulomb attraction, electrostatic attraction between the negative electron and the positive nucleus. But in addition to that, we have a repulsion between this electron and other 3 electrons, right? So there is a repulsion from this. There is a repulsion between this and that. And there is a repulsion between this and that. So these forces kind of destabilize the electron position. They make make electron to come further from the nucleus. But this force, it is stronger because it is a quadruple charge, positive charge here. And this force pulls the electron towards the nucleus. And this force pushes electrons from the nucleus. This is how it works here. In oxygen, we have the same situation, but there are 5 interactions instead of 3. But we have 6 plus charge in the nucleus. So we have a stronger attraction and stronger repulsion. Now the question is, which effect prevails? Repulsion from other electrons or attraction to the nucleus? So if we add the extra electron and add extra charge to the nucleus, what happens? What happens to this electron? Will it be more strongly attracted or more strongly repelled? And that is the question. To answer this question, we need to remember how the Coulomb law is formulated. Who remembers how the force, the attraction or repulsion force is calculated according to the Coulomb law? It is proportional to the charge of each. We have 2 objects electrically charged. So it is obvious that the greater charge, the stronger attraction. If we double the charge, the force doubles. If this charge doubles and this charge doubles, what happens to the force? It quadruples. It becomes 4 times stronger. 2 times 2. Who knows how much it is?
4.
Really? Great. The next question. What about distance? The distance, it is easy to explain like this. Imagine there is a charge and some kind of lines are kind of emanated from this charge, which is kind of a force. Each of them corresponds to a force. And let's take let's cut some square here at the distance the distance is r. And now let's double this distance. Makes the distance 2r. And increase the size of this square proportionally. So it will be 2 times bigger, right? And the same lines are crossing this square and that square. But this square is 4 times bigger, right? So this equals to that. Agree? That's a simple math, right? That means how many, if you draw many lines of that kind, and there are n lines which cross this square, how many lines cross the same square, the square of the same size here?
N? N number of lines?
No. N crosses the big square, but we are talking about a smaller square. The smaller square is smaller than the bigger one, and it is smaller, is 4 times smaller, right? That means how many lines are crossing the smallest square at the distance 2r?
N divided by 4?
Exactly. But if we imagine these lines like a force, attraction force, that means the force to the same object, attraction force, will drop 4 times. And that is a mathematical proof, actually. That's a serious mathematical proof that any force of that kind, which acts between one object and another object, the center of other object, is inversely proportional to the square of the distance. So this applicable to Coulomb forces, to gravity forces. If some other forces existed, then it would be applicable to them too. R square. So attraction is proportional to the charge and inversely proportional to the square of the distance. That means the further objects are, the weaker they attract each other or repel each other, and it is proportional to the square of the distance. And now, let me check the chat. Yeah, I see the answer. Who is it? Elizabeth, yeah, correct. Now, so going back to this story, the answer to this question is the charge does not change, right? The only thing that changes, I mean, in that case, the charge is something, the parameter. But what can change is the distance. Now, the question is, the nucleus, the position of the nucleus is well defined, but the position of electrons is not. That means the electrons may choose the position in such a way that they, at every concrete moment, they may be further from this particular electron than this electron is from the nucleus. And this is my lovely example. I love to use it. Imagine a ballroom. You have a party in a ballroom, and there are many people here. And they are moving randomly, they are meeting with each other, they are totally neutral to each other. So they meet each other, say hi, bye, and go further, right? And imagine there is a person, and so if we try to track their trajectory, it is totally random. And its average position is where? Who can tell me where the average position of each of those person is?
In the middle.
Yeah.
In the middle. In the middle. So we may assume that the average position between you, if you move randomly, and any other person is the at any moment is the distance between you and the middle. Now imagine a different, a little bit different situation. Some person came, so you are here, and some person came whom you hate, and you don't want to come closer. You continue moving randomly, but you choose such a trajectory that the distance between you and this person is maximal. And this person also recognizes you, and they also choose a trajectory which is random, but it looks random, but they try to be as far as you as possible. So when this person is here, you decide to be here. When this person is here, you decide to be here, and so on and so forth. If some observer try to track your position without knowing about this conflict, this observer would never recognize any difference in your behavior and behavior of any other person in the park, in the ballroom. But the average position between you and this guy is bigger than the average position between you and any other random guy. Do you understand why I'm talking about that? What do I mean?
Electron. That's like electrons.
Yeah, electrons, because they are moving freely, they have an opportunity to avoid each other.
Mm-hmm.
That means if you have an extra electron plus an extra charge, the attraction of the electron to the nucleus will increase, but the repulsion with other electrons will increase at less degree. That means the bigger the number of electrons in some shell, the more avidly they are attracted by nucleus, by the atom. So the atom becomes more electronegative. And this is a property of elements to hold the electrons. This property is called electronegativity. Now, what happens if two elements with different electronegativity make a bond? For example, when carbon and hydrogen, they have pretty much the same electronegativity. That means their common electrons spend approximately the same time near this atom and this atom. So this bond is pretty much non-polar. But if we replace this bond with, for example, CO bond, carbon is much more less electronegative than oxygen. Then the electron will displace to oxygen. They will spend more time with oxygen. That means carbon becomes partially negative. It's not an ion, partially positive. And the oxygen becomes partially negative. And this is the Greek delta, which means a fraction of charge, not a full charge. So this is not an ion. This is the kind of partially negative atom. So the bond remains a covalent bond, but the electronic density is displaced. So it's a polar bond. Usually we consider bond a polar bond, not ionic, when the difference between electronegativities of two atoms is 1.7 or 0.8, I don't remember exactly. And for carbon and oxygen, this condition is met. And due to that, due to the polarity of the bond, in addition to the stabilization due to sharing of this electron pair, we have an additional Coulomb stabilization. This partially positive atom is being attracted to partially negative atom, And that makes this bond more stable than this. And that makes HO bond more stable than CH or HH. So polar covalent bond are more stable than non-polar. And in our example, when methane was burning in oxygen, non-polar bonds transform to polar bonds, and so the overall energy of the system dropped, and the excess of energy released to the environment. Does it make sense? Great. Now, no questions so far. If yes, then we go to the last topic. If you have no questions so far, then it's okay. Then we move. Then we move further. Can I move further? Yes. Does everybody agree? Good. Now, how can we and now let's make a thought experiment. We know that sodium ion and chlorine ion, when they form a crystal, they are held together. But when they dissolve, they dissociate and form ions. Now imagine the same process occurs here. We break the bond and electrons stay with the atom, which is where they spend more time. That likes when, I don't know, two spouses divorce, right? The kids stay with the parent who they love more. That kind of, I don't know if it's a good analogy, but maybe that's. So if we break the bond and the electrons stay with oxygen, what charge these carbon gets? The charge becomes +1. This is not a real process. In contrast to this, in contrast to electrolytic dissociation, it is not a real process. That's an imaginary process. That's kind of mental exercise. But it is useful, and I'll explain why. Now imagine we do the same with all 4 bonds. We have when we cleave this bond, the carbon get 1+. When we cleave this bond, the carbon gets 1 more plus, the 3rd plus, and 4th plus. So the total state will be C +4, not 4+, but +4, because it's not a real charge. That's an imaginary charge. And this number is what we call the oxidation state. If in this process, the carbon gets a quadruple positive charge, then the oxidation state of carbon in CO2 is +4. That's not a real charge. That's not there is what may happen during electrolytic dissociation. This dissociation never occurs. But this is a formal number that demonstrates the oxidation state of carbon. Accordingly, the oxidation state of oxygen will be -2 here and -2 here. And this is normal. If we take some molecule and add all oxidation state of all atoms, we get 0, because the number of electron withdrawn is always equal to the number of electrons donated. Does it? Is it clear? Is this concept clear?
Yes.
Why do we need it? We need this concept to explain changes in again. If normally, if the oxidation state decreases, we call this atom is being oxidized. If you look at the classical oxidation, when the oxygen attaches to something, that's equivalent to combustion. But there are many other examples of oxidation. For example, which is much less violent, or is not where oxygen is not involved. Thus, our old example, when iron dissolves, reacts with the HCl. What's the oxidation state of iron in the iron nail? Who can tell me? Is it connected to any other elements?
Would it be 2+?
No, it is connected to other atoms of iron. So the situation is totally symmetrical. When the electrons are traveling among in the piece of iron, if you take some volume around the each atom, the average number of electrons here is exactly the same as the charge of the iron. So the net charge is 0. Normally, if some element is connected to other atoms of the same element in the free state, the oxidation state is 0, because there is no other elements to whom the electrons can be donated. Does it make sense? I can please say it out loud, because I don't see your faces when I'm sharing the screen.
Yes.
Yes, understand? Because there is no possibility, there's nobody to whom electrons can be donated or from whom electrons can be accepted. All electrons are here. So the state is 0. But when it goes to a solution and the electrons are taken by hydrogen, it becomes positively charged, double positively charged. So it is oxidation process. So this reaction, HCl plus iron, is oxidation. Another example, chlorine is very reactive metal and non-metal, and if it reacts with the iron burns in chlorine like in oxygen, and we get iron chloride. Chlorine is electronegative; it withdraws electronic density. So each chlorine atom withdraws 1 electron pair. So the oxidation state of iron is 3+. So we do have an oxidation here, although there are no oxygen. There is no oxygen is involved. In our case, which we in the experiment which I demonstrated, permanganate ion is this. So who can tell me what is the oxidation state of manganese here? Manganese is a metal, so it is not electronegative. Oxygen is electronegative. Oxygen withdraws electronic density. How many? What is the oxidation state of manganese?
+5?
1, 2, 3, 4, 5, 6, 7. 7, exactly. And what is the oxidation state of sulfur in the sulfide?
4 or +4?
+4, exactly. So this sulfur can have an opportunity to be oxidized. And actually what happens, sulfide takes some oxygen from manganese, especially in the presence of acid. Acids facilitate this process. Without acid, it takes just 2 oxygens, and 2 sulfide ions are used for that. And we have sulfate. As a result, we have a sulfate, SO4, 2 sulfates, and manganese dioxide. This is the brown stuff that formed in the first case. In the second case, in the presence of acid, this ion facilitate this reaction, and 4 sulfide molecules take away all 4 oxygens from manganese, and manganese becomes just Mn2+. So the oxidation state drops from +7 to +2. And that means 5 electrons are donated by sulfur here, and 2 oxygens. And manganese becomes reduced. So we have a, yeah, I forgot to tell about that. There are always 2 members, 2 components in the reaction. If something is being oxidized, it is an oxidizer, so this permanganate oxidizes sulfur, because sulfide goes from the state where its oxidation state is +4 to the state where it is +6, right? In sulfide, it's +6. Sulfate, it's +6. So this is the process of oxidation, right? Because oxidation state increases. And oxidation is occurred due to the reaction with permanganate, which is an oxidizer. So oxidizer oxidizes something, and the oxidation state of this species increases. In this process, the oxidizer is being reduced. So this process, when the oxidation state goes down, is a reduction. So accordingly, this ion is a reducer. So this is a kind of, you understand it? Oxidizer oxidizes, and during oxidation, it is being reduced. Reducer reduces the oxidizer, and during the reduction, it is being oxidized. And obviously, the reduction oxidation is the transfer of electrons from the more electronegative, less electronegative atom to more electronegative atom. And obviously, the number of electrons given equals to the number of electrons accepted. That means the total, the combined oxidation state change of all atoms is exactly what?
0?
Exactly, yes, it's 0. But then what is interesting here? When you want to see if some reaction, if some oxidation reaction is possible, if you have several compounds and you want to know which, if there can be an oxidation state, reduction oxidation reaction between them, you always must look if some atom has an opportunity to be oxidized. For example, in sulfate, for sulfate, no oxidation, no further oxidation is possible, because sulfur in sulfate is the maximal oxidation state, 6. But sulfide can be oxidized. So if we have a sulfide, then some redox reaction is possible. Similarly, if we have the element the compound where at least one atom is at very, very high oxidation state, it can be an oxidizer. And at the end, and what is interesting also that redox reactions, redox means reduction oxidation. That's a short for reduction oxidation. Redox reaction that involve transition metals are frequently very spectacular because you already see one example when the transitional metal like manganese change color during this transition, and many other transition metals also change colors. And just few examples of the reduction oxidation mixture. Potassium nitrate. What is the oxidation state of nitrogen here? Who can tell me? To do that, draw the structural formula. The structural formula is this. What is the oxidation state? Nitrogen is less electronegative than oxygen, right? That means oxygen withdraws electronic density. In general, oxygen withdraws electrons from anybody except fluorine. So what is oxidation state?
+5.
5. The highest possible oxidation state for nitrogen. So this is possibly the oxidizer. What is the oxidation state of carbon? 0. Sulfur, 0. And what this mixture is, who knows what it is? A black gunpowder, the mixture of strong oxidizer and a strong reducer. So even a small spark is sufficient to initiate the process when oxygen will be started, when sulfur and carbon take an oxygen from nitrate, and a huge energy forms. And the last example is this. Carbon, carbon. I don't draw carbon. This broken line means carbon. Who knows? Who knows what it is?
Looks like some organic chemistry, something from organic chemistry.
That's TNT.
Oh.
TNT, trinitrotoluene. Industrial and military explosive, because nitrogen here, oxidation state is +4 for oxygens, right? And for carbons, for most carbons, oxidation state is 0. So these carbons have an opportunity to be oxidized, and this nitrogen has the opportunity to be reduced. So the same molecule is both the oxidizer and reducer. And you need just the initiation, and it boom, and it transforms to N2, CO2, H2O, and a lot of energy. So, if you want to have, if you have questions, you are more than welcome to ask. If you have no questions right now, you can ask me later, you know my email. But these questions must not be directly related to the problems. If I'll see they are related to the problems directly, I will not answer. Otherwise, I will gladly answer. But if you want, you may ask something right now. No? Then good luck with your problems. See you later.
Thank you.
Thank you. Bye. Bye.
Yeah.
Bye.